Hello fellow students, today I prepared a very nice exam question from paper 1 back in the days in 2011 and 2009 regarding with the complex number. And what I like to do is to make a potential extension for the relation with something called the Maclaurin series and Fourier series. Using the complex number, you can utilize those techniques using the exponential or logarithmic function to find the coefficient of such a series. And then throughout the video, what you're going to be able to see is that complex number gives you great tools to find such coefficient of a series. So without further ado, let's get started. So let's take a look at this nice exam question from November 2011, which is a very also popular question for school summative. If I see I have 2011 question given as the following, what you have is the geometric series and the association with the infinite series of a sine. For me, it's very interesting because every time you deal with the complex number, it's very common for you to see somehow it's associated with either cosine and sine. So should you have done some complex number before, you realize it's really to attack with either real parts or imaginary. And so essentially what you're going to be assessed here is to see that here we gotta work with the imaginary parts of the series. Okay, somehow again I want to remind you, you're using the complex number and it's dealing with the sine or cosine. It's really just to work on the imaginary parts or the real parts. So let's take a look at on this problem here. So what we have to do is to show that the modulus of Euler form is equal to 1, which we can easily show by using the polar form, right, the cis form. And then the definition of the the modulus of a complex number is to find the square root of a squared plus b squared, where the a and b are the imaginary part, right? So now I can use the Pythagorean identity to realize that it's equal to 1. So if I have of the following geometric series, my common ratio here is going to be 1 over 3 e to the power by theta, right? And then I can look at the absolute value of this, which I just have to take out the the modulus of it, which is equal to 1 over 3, so it's just less than 1. So then you realize that its infinite is going to actually converge thanks to our definitions of the infinite geometric series. Right? I got the common ratio that is less than 1, so I'm very happy that it's going to converge. Okay, now let's try to find some infinity. Well, if I quickly remind you about the formula, it's going to be a1 over 1 minus r, where you realize my first term is the 1, and then my common ratio is 1 over 3 e to the power by theta, right? So I'm going to use that form here. And then what we're going to do is to, we don't like working with the complex number in the denominator, so what you are encouraged to do is maybe work with the conjugate, right? So let's try to multiply by the conjugate on the on the geometric series. But I want you to please remember, it's a very popular mistake that people often mistakenly write the conjugate of the denominator as 1 plus 1 over 3 to the power by theta, but it's not in Cartesian form, it's in Euler form. For the Euler form or the polar form, you only have to attack on the argument. So in fact, the conjugate of the complex number here is going to be 1 minus 1 over 3 e to the power of negative I theta. So I'm going to multiply top and bottom line. Then let's try to expand thoroughly. So if you look at the denominator, I got the 1 minus etc. And you realize if you look at the denominator here, the sum of complex and conjugate is really just the twice of the real part, isn't it? So for that one, it's going to be the twice of the real part, realizing that they are conjugate to each other, so it's going to be twice of the cosine theta, easy peasy, lemon squeezy. Okay, so then I'm going to be very keen on separating this, simplifying this even further. All right, by looking at the real imaginary part, because for the complex number, it's at the end of the day, I want to separate by the real and imaginary part. So in this case, the real part is going to be something to do with the 1 minus the 1 over 3 cosine theta, where the imaginary part will be just positive I sine theta, because it's going to be the multiple of I. Right, so that is beautiful. So let's go back to the series. So now, what I just did was taking the imaginary part of that infinite geometric series with the common ratio of 1 over 3 I theta, right? So I just took the imaginary part here, all right? So then if I just try to simplify on the right-hand side, maybe I will multiply by the 9, right? So that I don't have to deal with the rational expression either in the denominator or in the numerator. So on the right-hand side, I will have 3 sine theta over, 10 minus 6 cosine theta. All right, so that's great, but the question asked me to get just a sine theta and 1 over sine 2 theta, 1 over 3 sine 2 theta, so you got to multiply by 3 left and right. So if I multiply by 3 left and right, then you can get the desired expression. So then if I multiply by the 3 left and right, you realize that it's going to be 9 sine theta. Right? So thanks to the geometric series and realizing that something to do with the sum of the sines is going to be associating with the imaginary part instantly, right? So that is the first part of this problem. So this way you can derive more complicated series, on the other exams, right? So in another year, what you had to do, it's a very popular induction problem is to do with the trigonometric function, and you get to use either sum to product or product to sum formula to prove by induction. But right now, using this technique, realizing that sum of sines can be associated with the geometric series of the exponential function, you can actually prove the identity without using induction. Let me quickly show you what I mean by that. The method that we just did, right, getting the sum of sines or cosine is to deal with the imaginary part or the real part of the geometric series of the complex number, can be associated to a problem, question number 13 in 2016 November. Let's take a look. So in this problem, it's also a very popular school test. What we had to do was to prove this result on part C using induction, okay? But imagine I wasn't given this series. Imagine I had to deal with just the left-hand side, and I wanted to simplify, right? And I want you to realize, okay, hold on a second. For that one, actually, you realize, all right, if you look at the left-hand side, my friend, it's a bunch of sum of sines. A bunch of sum of sines can actually be associated with the sum of the complex number, but in the Euler form, imaginary. And realizing that this is going to be written as the imaginary part of e to the power by x, and then e to the power by 3x, and then e to the power by 5x, some of the odd terms, you realize that, oh, okay, hold on a second, this forms a geometric series. Maybe I can simplify this even further with the common ratio of e to the power by 2x. And I can use the geometric series formula to simplify. It's a great start to derive an identity even without being given without the result, right? So let's try to solve this problem not by the induction, not knowing this right-hand side, but using just the geometric series of Euler form and see if we can simplify further. So let's take a look. So we had a bunch of sum of sines here, realizing that, so that's my aim. I'm not going to prove this by induction, even though this was the exam set question. So if you want to try yourself, please try. It's a very, very beautiful problem because it uses the importance of a product to sum formula. But suppose I didn't know it, right? So now I'm going to start with the left-hand side, and I'm going to take out the imaginary part of this Euler form as we previously discussed, and you realize that this is the geometric series with the common ratio of e to the power of I 2x, right? So that is great. And what I'm going to do here is just to use the geometric series formula, right? So if I take out the common factor of e to the power of ix, right, then you realize it's going to be 1 plus e to the power of ix goes all the way up to, what is it, e to the power of I 2nx, right? With the common ratio of, it's going to be 2x. So the common ratio here is e to the power of I 2. And I got n many terms here. Oh, oops, sorry. So it's supposed to be 2n minus 2. So I got the, n many terms starting from 0 to n minus 1th term. So this is the, the geometric series of n many terms. The first one, so common factor is e to the power of ix, right? And I'm plugging the geometric series formula, right? So a1, 1 minus r to the power of n over 1 minus r is what we're doing in this series with the common ratio of e to the power of I 2x. That's what we're doing. So this is the result of the series, and of course I want to take out the imaginary part. But if you look at the series itself, it doesn't look so nice, right? So I mean, obviously I'm going to take the power n here by the property of exponent. I can just do the multiple, right? So that's okay. And this is what I have. This is what I have. But right now, eventually what we need to do is to take out the imaginary part, and this one doesn't look so obvious what's going to be the imaginary part. And then previously, for the first problem, what we tried to do is to multiply by the conjugate, especially in the denominator. You can certainly do so. You could have multiplied this by 1 minus e to the power of negative I 2x, and then the numerator also similarly, right? But however, this is not going to solve things so peacefully, because you have to do the distribution on the numerator and use a bunch of the other trig identity, for which I'm not very keen on, right? And I will tell you another technique that's very popular for hard exam questions to simplify whenever you encounter a problem with the sum or difference of the complex number. And then essentially what we're going to do is to use the hyperbolic identity. So let me quickly show you what I'm going to do. So every time you have, for example, let's say 1 minus e to the power of I 2x, okay? What I want you to do, okay, is multiply by 1. You're going to multiply a special 1 here, okay? But then the one I'm going to do is I'm going to do the ratio, okay, of half of the argument that I have in this complex number, which is 2x, sorry. So I'm going to use the argument x, but with the negative. So let's try to multiply by, what is it, e to the power of negative I over e to the power of negative ix. That's what I'm going to do. So same thing. So a over a, so that's just a 1. But if you distribute now, what you end up realizing is that I have e to the power of negative ix, all right, minus e to the power of ix over e to the power of negative ix, okay? But essentially you realize that this is actually to do with the conjugate, and it's a difference, all right? And sum of complex and conjugate, let me quickly remind you, was the twice of the real part, wasn't it? So this I would have gotten the twice of the real part of the complex. But if I quickly remind you, the difference of a complex and conjugate is twice of the imaginary number I and then the imaginary part of the complex number. So for this one, without hesitation, I know it is going to be negative, but because I'm supposed to have the ix in the front, so I just factorize by the negative. 2I sine x, simple as that. And this allows you, all right, this allows you to compute the form very quickly. And exactly what I just did, okay? So that's great. But you realize then it's more convenient if I actually have this in the front. So what I'm going to do is actually multiply by negative 1 top and bottom, so that you have the e to the power by 2 and x in the front, okay? And also, we can do that at the end, right? We can do that at the end. What I want you to see here is, so because I have now the 2nx and 2x, what I can do is to multiply the half of that argument and then multiply by the conjugate to induce the difference of a complex conjugate, which is going to be 2i of a sine of that argument, as we just had said. So for that one, because my argument is 2nx, you halfen it, and then you put the negative of that argument, which is negative nx. So then if you do the distribution, as you can see, this is what I've got. And then realizing that this is actually going to come out as 2i sine nx, very conveniently, sine nx. Very conveniently, we'll be able to find the real or imaginary part very quickly. Okay, let's try to use it on the other parts of the fraction and then see what we can do. But as I've mentioned before, maybe I don't like working with the Euler form in the back, so I'm going to multiply maybe the negative top and bottom, right? So that you can change the order. If it's just double negative, doesn't really make any difference, but it's just nicer form. And on the numerator, that's just going to be 2 times I of a sine of the argument x in this case. But unfortunately right now I still have that nasty form in the denominator, but now you know the drill. I like to use the technique that we just talked about on the denominator as well, so that we can induce the, maybe in this case also the imaginary part. So for that I'm going to multiply by I of negative x, right, on top and bottom. So if you do especially the distribution on the denominator, what would you get? I get the e of ix minus e of negative ix, which I can rewrite this as simply just 2i sine x, right? So that's very nice, right? So let's plug it in. So I've got that. Then fortunately now I can get rid of this common factor of a 2i. Very beautiful. So I got the sine nx over sine x, and realizing that this negative ix, so we multiply that here, and then realizing this product and that product of these two factors will just become 1 because it's reciprocal to each other. So I've just got this, right? 1 over what is it as a coefficient? E to the power of negative I and x. But it's reciprocal, so it can become positive argument like this, right? So that's what I'm gonna multiply on the fraction. So this is what I had started with. I got rid of a 2i, very good, and I got e to the power of I and x, right? And then realizing that the e to the power of I and x can be put into the polar form of a cis, and then you're gonna do the distribution. But when you do so, my friend, remember the whole point of this problem was to talk about the series of a sine x, sine 3x. I believe it went all the way up to sine 2n minus 1x. And I want to derive this identity using the geometric series of the Euler form. So what I'm trying to suggest here is that you want to look into the imaginary part because it's something to do with the sign. So I'm going to distribute. However, I'm going to be just keen on the the product of the imaginary part only, right? So it's going to be, therefore, that's the imaginary part of this identity, which is going to be same as the sum of the signs that we just derived. But if you look, I got the perfect square, and maybe it's not so nice because the result that I had to show was, I believe it was a 1 minus cosine 2nx. That was the right-hand side of the series, this, which was to be proven by the induction. But I got the form, but it's not exactly the same. But you know how to lower the power of a sign using what angle? Very good, the half angle of a sign, right? So realizing this is the half angle, derivable from the doubling of a cosine, I can plug it in on the numerator. Then voila, I get the sum of signs to be simply just the 1 minus cosine 2nx. If you plug that in our form, then this is the result that we wanted again. So that's the comparison, right? So that was the result that we wanted to show, realizing it is provable using the geometric series of the Euler form. But if it's something to deal with the sign, please make sure that you want to relate with the imaginary. But for the cosine, obviously, it would be something with the real part, vice versa. I think it's very examinable, especially for the paper 3, and then we can get some inspiration from early exam questions, such as the one from that 2011, right? So that was some identity that I wanted to show you, and then relate to another problem in 2016, which was also to do with the sum of the signs. All right, so yeah, as you can see, what we had. So what I wanted to comment further is this. So we learned a technique to deal with the sum of the signs, right? But for this one, especially in the 2011 November, it's an infinite series, and then we just show that it converges to sine theta over 10 minus 6 cosine theta. But here's the thing, this is now going to put a little bit of a difference between 7 plus student and high 6 students. So what I'm saying here is, you just solve this problem, you can move on, all right? But maybe you can ignite your curiosity, academic curiosity, especially in terms of math, that you found a new sort of expression of a sum of signs to be simplified as just a single form, and maybe I will be interested in seeing the expression in terms of a graph. Maybe you are going to be willing to put this on the GeoGebra and see how this is going to progress and how this is going to make any similarity with the 9 sine theta over 10 minus 6 cosine theta. This is going to put huge difference between students, right? Those ones who are going to be just chasing after questions, or one could see this problem from the higher ground, okay? All right, so let's try to put this on the graph and see how this is going to progress, okay? So this is just a sine function on the xy plane. And now let's have a look at another progression here. Let's have a look at the sum of first 2 terms, all right? Let's have a look at a few more terms, and let's try to add with the first 10 terms. And let's go for the next 20 terms, and on and on and on. But as you can see, this is quite interesting, actually, because you realize this is the sinusoidal, but also periodically, what I observe here is that I've seen some of the expression of this linear function, right? It's very similar to the linear function. I wonder what it is. Well, I had a bunch of sum of signs, but now I got some of this sort of seemingly similar with the expression of the linear periodically. As we increase the number of terms, the approximation gets similar. So for me, that's quite interesting. That's quite interesting. And I can compare with the 9 sine theta of 10 minus 6 cosine theta, which is the convergence of this. And from here, you can get some inspiration for your potential IA topic, because by no means this was the coincidence, right? So this could open a new horizon of a chapter that you can learn as an extra, or potential IA discussion or extended essay discussion, something called the Fourier Series. If you want to give a progression of a expression periodically, you can use infinite series. You can have linear combinations of this infinite series of a sum of sine and cosine to represent that periodic behavior of a desired function. And you can, I think it's always great to get inspiration from exam questions, because they usually give you those questions to sparkle your curiosity. So now let's have a look at some extension with the Fourier series, which is now in the field of the, for the purpose of maybe potential extension for the internal assessment or the extended essay, okay? But very relevant to what you just have done, right? To deal with the geometric progression of an exponential form, and then derive the imaginary part or real part to associate with the sum of the signs, okay? All right, so let me start with the geometric progression. So if I wrote as a 1 over 1 minus z, I want you to realize within the interval of convergence, this is going to be just a geometric progression, right? This is a infinite series. But now let's try to set up the z to be our e to the power by theta. So when you do the progression, and if you sub it in, you actually have to deal with the two things, right? You have to deal with the modulus as well as the argument, okay? So and then not only that, after having plugged it in, you can actually associate with the real and imaginary part of the complex number, of that complex expression, and then talk about the sum of the sines or cosine. So geometric progression of a complex number can actually give you a great insight of those infinite series of a sum of sine and cosine, but you have to bear in mind with the two things. Am I going to deal with the fixed value of the modulus, or am I going to deal with the fixed value for the argument, right? So those are the discussion that you can also give whenever you deal with this type of series. And then I just simplify it for you, right? If I do the same thing with the, 1 over 1 minus r e I theta, and what you can do is maybe multiply by the conjugate and then rationalize in the denominator, put it into the real part, real number for the denominator, separate by the real imaginary part, it's going to give you such expression. So let's say the function of u is a real, and the function of v is imaginary, okay? And as you can see, maybe I could have put this as just a 1 times r, e I theta, r squared e I 2 theta, on and on and on, and then maybe I can separate this thing by the real imaginary part to distinguish the sum of the sines and cosine. If you look at the red part here, I see it's going to be 1 plus r cosine theta, r squared cosine 2 theta, goes on and on and on. And if you look at the imaginary part, that's going to be r sine theta, r squared sine 2 theta, goes on and on and on, right? So that's great. That's wonderful. And then those series can be associated with this real imaginary part simply given by those infinite geometric series formula, but separated by the real imaginary part. But now it depends on the r and theta, you see. Depending on you're fixing the r or theta could give you different types of a series. So if you fix the r value, let's say r is equal to half, you are going to see then bunch of the trigonometric series converging to a function. If you're fixing the theta, then you're going to see some expression of in terms of r, which you can put it in terms of x, and becoming some sort of infinite series of a polynomial. And now you remember this as an infinite power series of infinite power series. Something to do with the function is something that we learn in the syllabus. It's called the Maclaurin series. On the other hand, or Taylor series, depending on the center. And then the sum of sines, we just mentioned that it's something to do with the Fourier series. And therefore, this geometric series could give you two different aspects. Whether you are fixing the constant to be the r, or theta could give you either Fourier series or the Maclaurin series or Taylor series per se. Okay, so let's take a look at this interesting example. So now we can do this as a geometric series, and depending on the real imaginary part, we can derive the cosine and sine. Let's say that we're going. I've said that I'm going to do the real parts of this function, but I actually wrote it in imaginary part. So I'm going to deal with the v function here. Okay, I'm going to deal with the imaginary part. So forgive me about the typo. Okay, so that's great. So let's take a look. So now I'm going to take out the imaginary part, but I'm going to focus on, let's say, that I'm going to put the theta to be constant, you see? So a bunch of sines and cosines will be given as a constant, and you're going to be describing things just in terms of r, but it will be sort of a polynomial because we saw the progression to be 1 plus r squared, r squared, r cubic, but you're going to find those coefficients of those polynomials, which now allows you to work with something called the Maclaurin series. So this was the imaginary part of that function, but I'm letting the angle to be fixed, right? If I put the power before and then you simplify things around, you realize that I got this function expression using this infinite geometric formula. It was 1 over 1 minus z, but I'm taking only the imaginary part of it. And not only am I taking the imaginary part of it, I'm letting the theta to be fixed. So now things are depending on the r. But we saw the bunch of the expression with the real and imaginary part. But now I'm going to deal with the imaginary part, but I'm letting the theta to be power before, where sine power before will give you just 1 over 2. Right? So then those are the coefficients of the powers of the r. So let's take a look. So then this is going to be the one that I plucked So this is the one that I'm fixing the angle. But for this one, I'm letting the r to be fixed. So now if I let the r to be fixed, your imaginary part, which is now can be separated into the two things, using the limit or the sum of the sines of the imaginary part. and that will give you the limit with the sign expression, which is to do with the Fourier series, right? So this is the Maclaurin series, and this is the Fourier series. Okay, so that's great. The geometric series with the complex number can give you different aspects depending on who are you fixing, and the angle to give you Maclaurin, or the modulus to give you the Fourier series. Okay, so that's great. Let's have a look. So what I want to do is, we plug that in. We had the function, I believe, was defined to be 1 over 1 minus z, but I could describe this as a geometric series, which is a 1 plus z, z squared, just goes on and on and on within the interval of convergence, of course. And then we had that expression, but we are very keen on separating between the real and imaginary part. So this is it. I put it into the polar form. I can do the De Moivre's theorem. I can separate by the real and imaginary part, but we define the v function to be imaginary part in this case. So I'm going to just take out the sum of signs. All right, that's great. And that expression should be the same as the imaginary part of the value that I just directly plug it into the limit. But now if I'm letting the angle to be fixed as a power 4, now everything will be described in terms of R's and some sort of a power series, which is to associate with the Maclaurin. So let's take a look. So in this case, this was a value that I had from the limit, but that can now associate with this infinite series, but I'm letting theta to be power 4. Now you can plug it in and it will be given as such. But you realize that this is actually the Maclaurin series of of this rational function that we have. Okay, so that's very nice, because imagine that I wasn't using this geometric series approach, but for finding the coefficient of the Maclaurin series, it, right? So for the function, if you want to describe as the power series, the sum of infinite series of a polynomial, what we had to do was to find the coefficient of the nth derivative, plug it into 0, divided by the n factorial, right? And that could have been very complicated, because if you look at this function here, it's a rational function. So to differentiate, you got to use repeatedly with the quotient rule, which is very complicated. But not only that, for example, if I wanted to find the coefficient of the r to the power of 9, I had to differentiate 9 times. Using the quotient rule just once was already a hard task, but if I do the quotient rule many times, when the things are getting bigger and bigger in terms of the power, it will give me just a very painful experience. But now you can see, using this geometric series, things can be solved way more beautifully, right? Once again, how difficult this would be if I had to use the derivative method to find the coefficient of the Maclaurin. Imagine that I had to do this, differentiating 98 many times and plug it into 0 just to find the 98 factorial. Would have been very painful, but now you see things were actually a lot quicker if we had used the geometric. But now let's try to fix the r, but now changing the theta will give you different series. But this time it's not going to be power series. This is now going to be infinite series of a sine or cosine, which is something to do with the Fourier series. Okay, so let's try to now set the r to be half. So now you see the coefficient are given to be constant, but now they are described by the infinite series of not the polynomial but the sine, the sinusoidal. And if it converges, this will give you some sort of expression of the periodic behavior of a function, which is called the Fourier series. Okay, the absence of a cosine wave in this function is because it was an odd function, right? So it's something you will be learning this if you are keen on finding the Fourier series using the for your internal assessment extended essay topic. So it's not a coincidence. It's not just aesthetically satisfying, but it can be very practical, right? Because I haven't defined the Fourier series here, but to find the coefficient of the Maclaurin, you have to differentiate. But to find the coefficient of the Fourier series, you have to integrate. The function, if you write it, you can maybe define it for your IA or extended essay. It's given as, we have to find the function can be described as just an initial term here, and then the sigma an sine nx plus bn, another sum of the even function. Those coefficients, of course, can be 0 depending on the even or odd nature of the function. And if you wanted to find, for example, the an, the coefficient, you have to do a very nasty integral if the function comes out to be quite challenging, of the following form, the fx times sine nx, right? So that's how you find the coefficient. And if you ask me why, okay, that's another whole discussion to derive it. But I'm saying, if you were to use complex number, we derive everything from within the geometric series approach. To actually pull out this integral for our function is not easy, right? This was a sine nx, and this was the function that I wanted to repeatedly describe in terms of the Fourier series, you have to do those integral, right? And it's not easy to integrate this, but it ends up giving you pi over 2 to the power of n, which is the expression of the geometric series, thanks to what we already have seen before, right? So it's easy to integrate. So complex number can actually make things more versatile, right? So yes, this is actually great. Now, similarly, unrelated topics such as the Maclaurin series and Fourier series can be connected together using the realm of the complex number, because it's to either you're fixing those R value or theta value can give you either Fourier series or Maclaurin series, okay? So now, so that was a first discussion that I wanted to give regarding with the complex number and the exponential form, both seen on 2011, 2016, and then we now learned a geometric series approach of the complex number, but you see that it can be further extended for the Maclaurin series and or Fourier series, and it's not a coincidence. You can delve into further with those topics and potentially make it for your internal assessment or the extended essay. Okay, let's have a look at the next part of the complex number and its application with the now the logarithmic function. But this was also seen on 2009 May paper. So let's take a look. Okay, and this problem on the question number 13, what you had to do was to be introduced with this logarithmic function with the complex number and discuss why it is actually not so nice expression in terms of the unique nature of the solution. So what I'm saying is this. So how they define the logarithmic function with the complex number is the following. Imagine I'm plugging the complex number in the log. Okay. Then this can be put it into the many different forms, but let's say that I'm going to put it into the Euler form, and that's rather nice, isn't it? Because you realize that because of the product, by the property of the log, I can make it as a sum. So it's going to be ln of r plus ln of e to the power by theta. Okay. But now using again the inverse function nature of the log with the exponential function, those I theta can come to the front. So this is going to be ln r times I times theta, where theta is the argument of the complex number, and then the r is the modulus of z. So that's how we define it, right? But this is unfortunately not so nice because it's not unique, you see? What I mean by that is if I had done with the ln of e to the power of I pi over 4, and I have a ln of e to the power of I, let's say 9 pi over 4, using that property, you see that the value is actually different, right? So it's a pi over 4i. This is a 9 pi over 4i. But as you can see by the periodicity, the 9 pi over 4 and pi over 4 in the Arctan diagram is the same, right? It's still on the Arctan diagram, both of them are located in the pi over 4 in the first quadrant with the argument of a pi over 4. So therefore, that's why the setting of the definition from 0 to 2 pi is not very nice. Okay, usually for the logarithmic function, you define from 0 to pi. Okay, that's why you have to show that it doesn't hold and things will be different depending on the value. Oh, sorry, from 0 to 2 pi is good because it gives you a unique circle. So I'm not allowed to use 9 pi over 4. You have to change that into the pi over 4 using this definition. All right, so that's quite nice, and let's see how we can utilize that complex number approach for the logarithmic. But I want you to realize the first half of the video was to do with the geometric series starting with the exponential. Maybe I want to do something interesting series with the logarithmic function also, but maybe not as a, the geometric, but something else. Okay, let's take a look. So in this one here, yes, I'm going to define the log complex numbers as the inverse expression of the e to the power of a complex number as this, but as we previously discussed before, it depends on how you define the argument because it may or may not be unique, right? So as you can see, depending on the periodicity, there are infinitely many expressions of the same complex number. So we usually, restrict in the domain from 0 to 2 pi. Okay, but now, yes, as I mentioned before, for the exponential, we use the geometric series, right? For the logarithmic function with the complex number, what I'm going to be keen on is to use the Maclaurin series. When with the log base e, so I'm going to express this as ln, is going to be an alternating series of the following, which is very sort of a similar expression of the exponential, but first, why is it different? It's alternating, and second, it doesn't have a factorial, but it just goes by the end, right? So please bear in mind, ln 1 plus x, the Maclaurin series is sigma n is equal to 1 to infinity, negative 1 to the power of n plus 1 times x to the power of n over n is the Maclaurin series expression of the log. Very good, okay? All right, so that's great. And let's see how we can use it for deriving something interesting using the complex number and logarithmic, right? So now let's try to set the, so if I plug in the complex number, we'll be given as such, no problem, easy peasy lemon squeeze, just using the Maclaurin series of log. And then, you know what, I'm going to go back to that 2000, what was it, 11, was it 2011? I think it was November 2011 problem, right? On the question part D. Okay, so we saw that this was somehow something to do with the Maclaurin series, the Fourier series, wasn't it? Because it was a sum of infinite series converging to a certain form. But for the logarithmic function, what you can do is you can actually describe an alternating plus minus, okay? Using the Maclaurin series of log, but using the complex number will give you the infinite series of a sign, but this time alternating. And let's see what behavior we can attain from that approach. Okay, so let's now try to plug the complex number in the logarithmic expression. So now I've got this alternating series. I want you to check it out. Alternating series of a sign, but I got the denominator as a 1, 2, 3, 4. But as you can see, it cannot be done by the geometric. Can't be done. Why not? If you ask me, sure. For the geometric, it was typically possible if one of them was fixed, the r, the modulus, or the argument, the angle. But in this time, as you can see, my modulus is changing 1, half, third, and fourth. The argument is also changing from theta, 2 theta, 3 theta, 4 theta, right? So that's not very nice. I cannot use the geometric approach. But for this one, what I like to take is to work with now the Maclaurin series of log and see how we can derive it. So yes, as you can see, this is a very similar expression of the ln of 1 plus z, isn't it? So, you know, what I like to do is maybe I'm going to let z, all right, to be just e to the power by theta, okay? But, you know, it's a sum of signs. What do you think? You know, what will be the next approach after having taken those complex number expression, but I want to somehow just induce the expression of a sign, especially the infinite series of a sign. Very good. For the chapter of the complex number, something to do with the sign is really just associate with the imaginary part. So after having plugged it in, I like to do the imaginary part of it, but let's try to simplify first. So now I'm going to take the z as e to the power by theta on the expression for the log. So this is what I've got, right? But I like to simplify left and right respectively. So let's try to simplify the left-hand side first. I'm going to let the log of 1 plus z as a, 1 plus e to the power by theta. And then taking the imaginary part will give you the sum of the signs that I want. So my job is to simplify this as much as I can, not only just using the Maclaurin series, but algebra of the log, especially with the complex number. Right? Let me remind you what was the definition of a complex number on the log. It was defined to be ln of the modulus plus I times argument of z, where z was defined from 0 to 2 pi. Okay? So if I now take, you know, I wrote it down in just the answer, but if I just quickly show you, right, 1 plus z is a 1 plus, all right, e to the power by theta. Okay, that's great. So if you take a look, you know, in order to find the modulus argument, it's probably better for me to see the real imaginary part or use the identity that we mentioned before, right? This is e to the power by theta plus 1 because addition is commutative. And maybe I can multiply, okay, by the conjugate, half of it, on top and bottom, so that we can derive the hyperbolic identity on the complex number, which is going to generate either giving you, what is it, the twice of the real part or 2 times the imaginary part of the complex number. So if I now do the distribution, the technique that we learned from the first half of the video, this is going to be e to the power I theta over 2 plus e to the power negative I theta over 2. That's great, okay? And on the denominator, I got e to the power negative I theta over 2. That's wonderful. But if you look at the numerator, that's the sum of the complex and conjugate, which is going to be twice of the cosine theta over 2. All right? And whatever the identity that I had for the complex number, but it was in the bottom. If I reciprocate, the argument will be multiplied by the negative, becomes a double negative, hence positive. It will be, what is it, multiplied by e to the power I theta over 2. That is great. Right, so now the 1 plus z, all right, can be put it into 2 cosine theta over 2, which is my modulus, by the way, right? And then the argument, the complex e I theta over 2. So if I take the log on it, using the definition of the complex number inside the log, it's going to come out as ln of whatever the modulus that I have, which I'm not really interested in because I wanted to just associate with the imaginary part because I wanted to derive the infinite series expression of the sine. And then I'm going to add this by I theta over 2. Alright, so the imaginary part will be the I times the argument of the 1 plus z, which now becomes theta over 2. So that's excellent. So I got the expression of the theta over 2. That's the imaginary part of the ln of 1 plus e to the power by theta. But now the imaginary part on the other side with the infinite series of exponential was a sine theta minus half sine 2 theta plus 1/3 sine 3 theta, etc., etc. This will be just theta over 2. So if you try to put this on the GeoGebra or your graphic calculator, you see the periodic function of theta over 2 will be visible periodically from negative 2 pi to, well, I think it's going to be from negative pi to pi. Depends on how you set up the period. But let's have a look. Let's try to set up, right? So if I just quickly give you the graph version of it, the sine theta was this. But remember, I'm now doing the alternating series, so sine theta will be subtracted by half sine 2 theta. Let's see what behavior we get, and then add it by 1/3 sine 3 theta, and then you keep adding this on and on and on. And that's the first 5 terms. Now let's try to increase the number of terms because this is meant to be the infinite series, so the more terms you add, the more accurate it's going to be. So let's go with the, what is it, some of the first 10 terms. Let's go with 20 terms. And let's go with the 50 terms. So as you can see, it's got the behavior, a periodic behavior once again of the linear function. Oh wow, that's great. And now, not only you realize that this is somewhat the periodic function of a linear function, you already know the function. This is a theta over 2, wasn't it? Right? If you actually try to find the value, you realize that the gradient will be the half in this case. That's actually marvelous, isn't it? Because now we saw the infinite series of a sine, which I couldn't do using the geometric series because those amplitudes already, the modulus and argument were changing. But instead of using the geometric series, for the second half of the video, we learn about the role of a logarithmic function, but now I use it as a Maclaurin series. And using that for this alternating series behavior, I can derive this periodic function of linear function again, thanks to the Fourier series. I didn't do any of the what is a nasty integral. For this one, if you wanted to do, you were to find these expression using the integral expression of the definition of the Fourier series. Finding the coefficient is going to be the following. This is an odd function, so this would be given as a series of an sine n theta, where you had to derive this coefficient using this integral from negative pi to pi of theta over 2 times sine n theta, right? So you had to deal with this integral, and for this, maybe you were to use integration by parts and whatnot, but thanks to the Maclaurin series of log and the definition of the complex number on the logarithmic function, we can derive it very easily, okay, without doing this heinous act of the integral, okay? So, you know, this is inspiration again from the 2009 exam paper. I want to remind you that, you know, they don't give you those exam questions as just entertainment. There's always, I mean, obviously I think it's entertaining to solve those interesting problems, but if you now understand, if you realize the historical significance of those problems, it gets more interesting, and furthermore, it can give you more inspiration for your potential topics for internal assessment or the extended essay. Okay. All right. So for the finale of the problem, now I'm going to use another application of a Maclaurin series of log, but this time I want to derive the Maclaurin series of arctangents. Okay. All right. So you know, arctangent x is very similar to the Maclaurin series of sine. If I just quickly remind you of the Maclaurin series of a sine, it looks like this, guys. The sine x, okay, is an alternating series of x to the power 2n minus 1 over 2n minus 1 factorial. It is not alternating, and it's got a factorial, so convergence is very fast. But if you look at the arctangent, it's an alternating series, but also it doesn't have a factorial, as we discussed for the logarithmic function. And I'm going to discuss, if I let the x to be z to be ix for my logarithmic function, the complex number, we can easily deduce the Maclaurin series of arctangents without using actual differentiation. So let's have a look, okay? So, yep, I'm going to let the z to be 1 plus ix, and I'm going to plug that into the log. But what I want to remind you here is how to find the modulus argument. So, you know, modulus is the square root of a squared plus b squared, where a and b are real and imaginary part of the complex number. And then the argument is going to be, let's say, tangent theta is going to be just x over 1. So arctangent x is going to be the theta that we have. Right? That's great. And I'm going to put that into the logarithmic function we had. Remember, ln of z, thanks to the 2009 exam paper, we can put that as a ln of the absolute value of the z, which is the modulus, plus the I times the argument of the complex number, where theta was defined from 0 to 2 pi to give the sense of uniqueness into this expression. All right, so that's what we have. The now argument here is it was defined to be the arctangent x, where the theta, right? So that's great. Okay, that's great. But not only that complex number definition, I'm going to use the Maclaurin series of log. Remember, ln of 1 plus x was very similar to the exponential, but it's not alternating. It ain't got no factorial in the denominator. So then I'm going to put the ix as a substitution. So you get that, you see? But again, the beauty of the the complex numbers to associate separately by the real and imaginary part. So for this one, for the odd power, I'm going to group it for the imaginary part, you see? All right, so that's what I'm going to associate. But for the even power, thanks to the imaginary number, perfect square is a -1. We just give you the real part. The even terms are going to be the real part. So that's great, okay? Now you know the drill, right? I had the argument, so just before I continue, right? I want you to sort of remind yourself, ln of 1 plus ix was whatever the ln of the absolute value of I, but then the argument was arctangent x, so theta, okay? Now I wanted to derive the Maclaurin series of arctangent theta. So what I'm going to do is to use just the imaginary part of the infinite series that we just discussed, and then make that as equivalent, because that's the imaginary part of one way or the other, right? So that's the imaginary part here, but the imaginary part on the complex number definition of the log was the arctangent x, which was a theta, was the arctangent x. So as you can see, if you make this one and that one equivalent, then voila, that's the expression of the Maclaurin series of the arctangent x. So that's a wonderful, wonderful, another way of deriving those Maclaurin series. So, for today, we briefly discussed how to use the complex number with the Euler function and somewhat to do with the geometric series. And by fixing the modulus or argument, you can derive either, if you fix the modulus, we derive the Fourier series, which we had seen twice on the exam, and historically perspective of the IB curriculum. If you fix the constant, then you get the Maclaurin series of a very nasty rational form, which now I don't have to do the differentiation to find those coefficients, because it will be given as just a geometric series. That's very great. That was the first half of the video. To realize, yes, the Maclaurin series is to find the coefficient using the differentiation. The Fourier series is to find the coefficient using the integral. However, it can be put interactively, collectively, with the name of the complex number. But the second half was also to gain some insight of a complex number. But now, who played a significant role of determining the series was a logarithmic function. But I didn't deal with the geometric series for the logarithmic, but I deal with the Maclaurin series. And using that, we saw the periodic linear function from negative pi to pi. That function is called a Sawtooth function. It's a very typical example that you discuss in the Fourier series, but I didn't have to integrate. It's the beauty of using the complex number. But also, not only deriving the Fourier series with the log function, with the complex number, I derived the Maclaurin series, my friend, of the arctangent, again, without using differentiation. So complex number can skip the whole parts of differentiation or integration if you get the question correct. Okay, and yes, this is just the start of initiating your sort of inquisition. So not inquisition, sorry, of your research for your potential beautiful topic for the extended essay or internal assessment to do with the complex number and the Fourier series or the Maclaurin. Okay. But yeah, that's pretty much it for me today. As you can see, there are many, many interesting topics throughout the history of IB exam questions. So I'm really keen on finding them, okay? And let's please get through more interesting topics to be discussed later, okay? That's it for me today. I will see you next time. Thank you for watching. Thank you.